the part on theoretical basis of the certification. Theory. Chapter 2, thermodynamic of solidification. We repeat and extend something from the previous course kinetic processes in material. We review, we extend the content of this chapter. Then nucleation, chapter 3, and then solid liquid interface. Okay. And dendritic solidification, chapter 5, and chapter 6, authentic solidification. So this is the end of the part 1 theory, and the part 2, the defect. This is defect related with the solidification processes, such as microsegregation, microporosity, hot theory, and macro segregation. It's the defect part 2, and finally we have the chapter 11, controlled solidification processes. So we have 3 parts. So I will teach the first introduction, first part, and then Dr. Nguyễn Hồng Hải, the same name, family name as mine. Okay, for 5 weeks, we'll teach you the defect, the part 2, and then I will teach you the last chapter, control solidification process, about 2 weeks. This one about 8 weeks. Okay, and after this we will do the midterm examination. The midterm examination is the test plus some exercises. And the final answer, the same form. We have about 35 questions, test questions, and then we will have maybe 2 exercises. This examination. Okay, this is the content of our course, certification processing. And the textbook is the main textbook. Very good book. Fundamental of certification. The author is HUST and Fisher. You can find it in this book in maybe the internet, maybe. And you can find my book, certification processing. Okay. It's a main textbook. And you can have some references, such as Menton Fleming, solidification process. He's a professor from MIT, Fleming, very famous professor. Fleming. You can refer to the solidification course. The author by transformation in methanol, also very good book. This Japanese Professor Ono, the certification of metal. And then we have maybe certification and gas structure. HUST also. HUST, yeah. Engineering heat transfer, and maybe crystallization technology handbook. Okay, some references. So we turn on the relative position of certification processes. So we know this cycle. I didn't this cycle already in the previous course. So we can see it is the physical space of material, physical space, and in the center is the chemistry. I mean, it is the chemical composition of the material, of alloy. Okay, and this chemical composition can determine 70% of the chain of material. 70%. 70% of the chain of material of alloy come from chemical composition. So the rest 30% where come from? It's from processing. From processing. What we have the type of processing? Maybe crystallization, solidification, deformation, heat treatment, and so on. Right? A lot of the kind of the processing. So this 30%, the rest percent of the chain come from the processing. See, but it is more difficult, much difficult. 70% from chemical composition, 30% from processing. And this chemistry, chemical composition, and processing will determine the structure of the metal, of the alloy. See, structure is the microstructure. Is the size and morphology of the grain, lattice defect, and so on. Structure. Okay. Chemistry, processing determine the structure, our microstructure. Is the size and morphology, sign form of the grain, lattice defect. So in this structure determines the properties, such as chain, hardness, activity. These properties and performances, such as fatigue, grip, corrosion, and air resistance, and also so on. See, and these two almost properties and performances very strongly related to the environment. This almost cycle properties and performances very strongly related with the environment, and corresponding to this physical space material, we have the MSE subject, machine science and engineering subject. Okay. Also 5 cycle. So we have the thermodynamic corresponding to the chemistry, kinetic, crystallography, okay, properties and performances. See, you have some the subject of the machine science and engineering corresponding to the physical space of material. And our course, where is our course? Of course, kinetic solidification process. Yeah. Belonging to the processing, solidification process. And we know that the difficulty of the subject increase toward the center. So our course is rather difficult, not easy. See? Okay, it is a relative position of our course, certification processing. So so now on the first chapter, introduction, and the first part is the importance of certification. Why you need to study the certification processes. You see that certification is phase transformation from the liquid to solid state. It's the phase transformation from liquid phase to solid phase. Okay? That involves the manufacture of almost every man-made object. Every man-made object. For example, you can see you know this? Copper drum. Okay? Or maybe you know this? It's the Statue of the Liberty. It is in New York. I have been there for some time, or 2 times. And maybe some mechanical paper. See? So on this man-made object is related with the how to make them by certification and crystallization process. Okay. So one of the major practical application of the certification is casting. Casting, the major practical application. Very economic method for forming a component. If the melting point of the metal is not too high. Then on 1006 and 360 degrees Celsius, is maybe steel. If you make something from steel, cast iron, copper, bronze, aluminum, and so on. So the certification process is a very economic way to do this. Why? So you can see and pay your attention in this graphic. It is viscosity versus temperature. Viscosity is dynamic viscosity. You know there are 2 kinds of viscosity: dynamic and kinematic. So we have this coordinate. We have viscosity and in FC temperature. So you can see from this graphic, the viscosity increased very much from the gas and liquid state to the solid state. If the viscosity of gas and liquid is very low, but if it transforms into the crystal, to the solid, so the viscosity is increased very much. If crystal can form, so the viscosity increase with a sum from very vertical sum from the very low value to the very high. And if the crystal do not form, and we have glass amorphous, so we have the increase is smoothly, more smoothly. But if the crystal form, you can see we have the very sudden increase of the crystal. So if This could be very high. We pay a lot of energy to make the detail, the component. So it is more economic to make the detail, the component from the liquid. More economic. It's why the solidification and the major application is casting is the most economic way to make the component. And for solid, very high flow strength for solid metal. But for liquid, almost zero strength, shear strength, almost zero. So we can save a lot of money to make the component from liquid state rather than from solid state. And solidification pattern drawn in microstructure forming, and then improving the quality of the product. You can refer on this. Second, we have the processing in determine the structure. Chemistry, that's processing. Okay. So solidification is the pattern drawn in the microstructure forming. Chemistry, processing, and we have the structure. Determine the property and purpose. It's the loop. You have the example of the cast iron. You have in this coordinate, you have the chemistry or chemical composition. It's a percentage of the carbon. It's carbon in the cast iron. It's a chemistry, and in this axis, we have the solidification rate. The most characteristic parameter of the solidification process is V, the processing. So we have here, we have chemical composition or chemistry, and in axis we have the processing, and represented by solidification rate, and the unit is millimeter per second. So success, we have the same composition, chemistry and processing, and we have the same composition. For example, 3.6% of the carbon. 3.6% of carbon. So depending on the processing parameter, is solidification rate, you can have the absolutely different structure, different microstructure. If the solidification rate is low, we have the carbon in the form of the graphite, and we have a gray cast iron. And if the solidification rate is high, we have carbon in the form of the cementine. And you have the white cast iron. And white gray cast iron is in the middle. Okay, so this gray cast iron is graphite, and white cast iron is cementine. In the structure, they have the absolutely different properties. and performances. It is a very good example for the microstructure forming, depending on the processing parameter. So in this, if you pay your attention in this picture, you can see that the higher percentage of carbon and the lower silication rate, we can have gray cation. Yeah, it's a gray cation. The domain of gray cation, and the lower percentage of carbon and the higher solidification rate, we have the white cation, and we have carbon in the form of the cementite. So graphite is a stable form of the carbon, and cementite is an unstable form. And with the time, the cementite will transform the graphite. But the time for transformation from cementite to graphite is very long. So nowadays you can consider the cementite as a stable phase, also stable phase. So you can see here in this slide the influence of the processing on the structure forming or microstructure forming of the alloy. And you can this solidification index is very related with the cooling rate, but it is a different thing. The cooling rate and the solidification rate is a different thing, not the same. But you can see here dependent of the microstructure on the cooling rate. And so the another characteristic parameter of the solidification process is also the processing parameter. So the cooling rate, it is the unit is the Kelvin degree per second. So can pay your attention. The unit of the solidification rate is the millimeter per second. But for cooling rate, we have the Kelvin degree per second. So it is a very large range of the cooling rate, very low, 10 power minus 1 degree per second, until much higher, 10 power 8, maybe higher degree per second. So for from liquid, after crystallization and solidification, if the cooling rate is very low, we have the conventional microstructure, about 1 degree per second, the cooling rate. We have the conventional microstructure, and we have the coarse dendrite or synthetic. If you increase the cooling rate until maybe 10 power 4 degree per second, so we have the much finer microstructure, and we have the fine dendrite or synthetic. And if you still increase this cooling rate until maybe 10 power 6, so we have new microstructure. See the dependence of the microstructure on the cooling rate. And if at the high cooling rate, you can have the superfine mitochondria, quasi-equilibrium phases, amorphous. The microtexture can change from very coarse to the amorphous state. No crystal, no tie to form the crystal. So texture is in the amorphous state because the cooling rate is very high, very long, very short time for solidification, and the crystallization not have time. No time for crystallization, no time for crystal to form. Okay, so we have some amorphous, and you can see that increasing microstructure homogeneousness of the microstructure will increase if the cooling rate increase. At high cooling rate, we can have the more homogeneous structure. More homogeneous structure can form at higher cooling rate. And on of this microstructure is depending on the composition and technology. So, dependent on the microstructure of the cooling rate. So we our task to obtain this structure, maybe something by dendrite, maybe superfine phases, maybe quasi-equilibrium, and in some cases we want to reach to obtain the amorphous. It is in some cases. And the question is how to create such a high cooling rate, very high. It's the question of technique. And you can see the effect of the solidification. It's very evident. And casting is the casting is the final operation. Okay. You can see here the dependent of the mechanical properties, strength, sigma, and elongation. The dependent of this upon the fineness of microstructure. Here in this coordinate, you have the ultimate trend and elongation by percent and megapascal. Here we have the axis. We have the dimension of the sample, the bar, maybe the radius of the bar, the sample, the specimen, and you can see if the larger the dimension of the component of the casting, so the microstructure is coarser. And microstructure is represented by this parameter. It's a secondary dendritic spacing. Secondary dendritic spacing. It's denoted as a lambda 2 and by micrometer. So you see if the dimension of the casting of the component is larger, so the cooling rate will be lower. So if the cooling rate lower, solidification is lower, so the microstructure in the cursor. It means the secondary dendrite amplification increase with the dimension of the casting. And if the microstructure become coarser, so the property mechanical property decrease. The coarser microstructure, the lower mechanical property as intermission and elevation also. All of them decrease. See? The reason because the microstructure become coarser. See? Because you have this this relation, the trend of the metal of the alloy is inversely proportional to the size of the grain size D. P in sigma 0, which is some coefficient. So the coarser microstructure, the lesser grain size, the lower trend and other mechanical properties. See? You can see here, for example, R is here. The last, so we have the grain is very coarse. So we have the coarse microstructure. Its R is small. We have the high cooling rate. We have the very fine microstructure. Then we have higher mechanical. Okay, so the greater dimension R of the casting, the slower cooling rate. The heat must be transferred from the inside the environment. Okay. The slower cooling rate, the coarser microstructure, grain size, and the worse properties, lower value of the ultimate trend and elevation. So we have to create the verified microstructure instead of the coarse. So how to create the fine microstructure is a very important question. How to create the fine microstructure? We have the answer here. Here, fine microstructure. So we have to increase the cooling rate and solidification rate. Okay, this is the answer for this question. How to create the fine microstructure to improve the mechanical properties. See? And another feature of the casting is the defect. This defect, once formed during the fabrication, is very difficult to eliminate. Very difficult. Impossible mission. Too difficult to eliminate the defect once they are formed during the fabrication. You can see the example we have the slab here. After casting, we have the surface segregation. In the inner part, we have the dark color, and in the outer part, we have the lighter color because of the segregation. Because here we have some another element than in the same. So it's a segregation, surface segregation. And after it is after casting. and you have the defect as a segregation. But after a lot of the step of the fabrication, we have this as a product, but the defect remain. After deformation, a lot of step of the deformation processing, but see the defect, the surface segregation remain. Cannot be eliminated. So it's very difficult to eliminate the defect once they are formed. See? So the task, do not let them form. It is our task. Prevent their formation. Do not let the segregation to form or in another kind of the defect. Okay, so we can see the solidification is related with the properties, okay, with the defect of the product. And the third reason, the crystallization of certain pure substances, very, very great importance, because we can make a semiconductor. For example, the semiconductor create silicon crystal and integrated circuit, new electronic device, and so on. So this is why you need the preparation of large single crystal of very high perfection. Like this. You can see this. What is this? This is a single silicon crystal. Silicon crystal. And we need it for maybe solar battery and other applications. It is only one crystal, single crystal, very large single crystal, and prepare for by some very specific method. It may be 2 meters of the height. So the preparation of the very last single crystal of very high perfection. And at the moment, such crystal can only be produced by grow from the man. I grow from. There is no other method. That to crystal, the man to crystalline, and then we are only one crystal can be developed. Only one. It grow from the man, or this by the crystallization process. So this is why doing the solidification involves from the purely technological and empirical field to become the science. From the technological and empirical to science. So I will need to learn, study the solidification theory. So the two most important tasks of the solidification theory. First one, determination of the solidification rate. In some literature we have the terminology flow rate. V, meter per second. And then most characteristic parameter of solidification process. Solidification rate. And it is very strongly related with the cooling rate. And clarify the second task. Clarify the relation between solidification rate, structure, property, and performance of detail of the casting made of different metal and alloy. Okay. So firstly we have to determine this parameter, most characteristic parameter of solidification and relation between it with the structure, property, and performance of the alloy and metal. Yeah. We have the solidification rate is here in the processing cycle. Okay. And this is related with the structure and properties, performance of the alloy. So we have two tasks of the solidification. And there are a lot of the physical phenomena to be controlled in solidification. See, a lot of the physical phenomena, such as diffusion, morphological instability, interface thermodynamics, capillarity, buoyancy effect, electromagnetic effect, and convection harmony, turbulent flow, and so on. A lot of the physical phenomena to be controlled. But because solidification, it is a transformation from liquid to solid. Maybe crystal, maybe not, but from liquid to solid. And there is an interface between liquid and so solidification is here. Okay, because it is a transformation from liquid to solid. So we pay our attention only to four phenomena: interface, thermodynamic, diffusion, capillarity, morphological instability. And this another phenomena maybe can be studied in another courses. Maybe such as mechanics of fluid and maybe some other courses. But in our courses, so solidification processing, we pay our attention to only four phenomena, physical phenomena related with the interface between the liquid and solid. Because solidification, it is a phase transformation from liquid to solid, from liquid to solid, and solid may be crystal, maybe amorphous, maybe, but in general, the crystal can form in this form. So the solidification theory is theoretical basis for some technology. And firstly, it is for traditional technology, conventional technologies, such as casting. We can have some kind of the casting, as continuous casting, ingot casting, precision casting, die casting, sandwich casting, and so on. Casting is application in the whole volume of the detail. Casting and bending. We have a lot of kind of the method of the bending. Arc bending, resistor bending, plasma bending, electro beam, laser, and so on. And bending, it is not, it is a solidification, but not in the entire volume of the detail, but only in some part of the detail. The casting, the solidification occur in the whole volume of the detail of the component. In the case of bending, the solidification happen in only some part, not whole volume. Okay, and we have advanced technology. Solidification theory can be theoretical basis for some advanced technology. This is semi-solid technology, semi-solid, such as rail casting, tissue casting, and so on. Rapid solidification. We can have main spinning, atomization, band undercooling, surface remelting, and so on. Rapid solidification technique. We can have also the directional solidification. Is for making directional solidification. Is for making this one, the single crystal. This one is the application of the directional solidification. Okay. So we have rapid solidification. We have directional solidification, such as Bridgman furnace, Chogransky method. Is the single silicon crystal we have seen. It is prepared by Chogransky method. Bridgman furnace and electroslag refining. This is a very high cooling rate for rapid solidification. For this technique, the cooling rate is very low, the opposite to the rapid solidification. Okay. And you have surface treatment by laser. It can maybe the composite composite. So it is an advanced technology based on the solidification theory. The solidification theory is the basic, theoretical basic for this technology. A lot of it is the main way to create the component, the detail. It's very high properties. Okay. So we have the traditional and advanced technology on the basis of the solidification theory. A lot of technology. And we see now the level of the structure study. The level from the very high, very cost level. It is in the meter. It's casting. The ingot casting like this. Okay. If you magnify this part, you can have this. You can have this. It is a macro level. It is a system level, and you have macro level about in the level of the millimeter. So we have the here. We have the transport phenomena: mass, species, heat, and momentum. We have here we have macro segregation, porosity, some defect related with the solidification processes. See? Yes. The macro level. We have the crystal level in some about in the range of about 100 micrometer. If you enlarge, magnify this part, we have the dendrite here. We have the columnar dendrite in the left, and we have the equiaxial crystal in the right. See, we have magnified, enlarge this part. So at this level, you can study columnar or equiaxial crystal, attraction of the latent heat, dendrite arm spacing between the dendrite arm, and the distance between them is the dendrite arm spacing. Local heat and species transport at this level. So if we magnify the tip, the dendrite tip, here, you can have this. And at this level, it's a micrometer level. We study the solid liquid interface. It's a solid liquid interface level. See? We here at this micrometer level, we study the instability of the solid liquid interface, capillarity effect, undercooling, growth of phase boundary, and grain boundary. Yeah, at the micrometer level. And finally, we have the atom level in the nanometer level. Here you can study nucleation, kinetic, and of molecular attachment. If you magnify the dendrite tip, you can see. So, see, you can distinguish high level to study the microstructure of the alloy. Atom level, nanometer, solid liquid interface level, micrometer, crystal level, about 100 micrometer, macro level, millimeter, and system level. And I would like to so that will pay the attention at its macro level. So here we have some transfer phenomena: mass, species, heat, and momentum. So we study our course. We study in our course. We study from the bottom up, from the atom to nucleation to micrometer level. It is the interface. Okay, nucleation, interface, and crystal formation. Maybe dendrite, maybe authentic. We in our in our course, we studied three levels, from atom level to crystal level. This level, macro level and system level, you can learn in the other courses, not in our. And we go from the bottom up. Nucleation, interface, insulinic and crystal formation, and dry, synthetic, and so on. So, but I would like to pay attention in the macro level. Here, because here has some transporter phenomena, mass, acid, heat, and momentum. So now to describe any phenomenon, physical phenomenon, we can use the two kinds of the law. Firstly, is law of the conservation. Law of conservation. Conservation of mass, conservation of species, of heat, and momentum. And totally, you have only 4 law of the conservation. And most famous is the conservation of the energy. Okay. And you have the law of behavior. Law of behavior is some for example, Bury, Newton, Stephen Boltzmann, Bernoulli, Navier, also numerous. Why we have only five laws of conservation? We have numerous law of behavior to describe any phenomenon, physical phenomenon at the macro level. See, but we study this is another courses. In our course, we will pay attention in study only three level. Into formation of the crystal. Okay, and we go bottom up. See here. Okay, and it's some example of the system level. We have the part component, the mechanical component. It's a pump cover. And at the micrometer level, we have piston, and dry. It is the grain, and we have the crystal level, at crystal level. And it's atom level, nano level. Okay. For simplicity, we can classify, can distinguish only 3 levels instead of 5. System, micrometer, and nanometer. If we distinguish only 3 levels, so we will come only to the bottom to this one. From the atom level, nanometer, the micrometer, to the formation of the crystal, and dry, grain boundary, and so on. The dendriam spacing, the distance between the dendriam, and maybe the grain, the size, the form grain, the form of the boundary, and so on. Is the crystal level. This is the level. There are another process. Okay. So, for the nanotechnology, in our department, in our institute, we have some route, some way to make the nano structured material. For example, the mannequin alloying from myelin. Mannequin alloy is some research on the department of the non-ferrous metal, the mechanical alloy. Maybe some another method is severe plastic deformation, SPD, equal channel angular processing. This we have some top research in the department of the metal form. And crystallization and certification by rapid certification to firstly to obtain amorphous metal, and then crystallization to obtain nanostructure composite, for example, or maybe in situ processing of the nanostructured material. So by the crystallization and certification process. So it is in our department of foundry technology and material, and we are now studying this process, crystallization and certification. And there's another way, the nano powder by electric explosion of wire. So there is no, not at any research in our institute. Maybe we will do something, some research on this topic. Nano powder, we can create, prepare the nano powder by electric explosion of wire. So it is the route, the way to obtain the nanostructured material, in our institute. Okay. Do you need some rest? Hello.
Yes.
Do you need some rest?
Yes.
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 Okay. Okay. So we have the rest for some minutes. Okay.
Okay.
15 minutes.
10 minutes.
10 minutes. Okay.
Okay. Have some rest. Hello, let's continue.
Yes.
Okay. So we have the have stopped at the way to create the nano structure function in our to know on the solidification process. So for solidification, the heat must be extracted. So we are learning now the heat extraction from inside to the environment. You can see, you can pay your attention in this. This graphic already the dependent of the energy, enthalpy, the internal energy of the system on the temperature. So the various solidification process involve the extraction of the heat from the main, of course. So the solidification can be processed, and there are two ways to extract the heat from the main. Okay. And the heat extraction change the energy of the phases. Two way. First one, the decrease in the enthalpy of the liquid or solid due to the cooling. By this, now the change in the enthalpy is the integral of the capacity, heat capacity, with respect to the temperature. So it is decrease in enthalpy. We have the interval DC. It's a decrease of in enthalpy of the liquid, and BI, the decrease of in enthalpy of the solid. So the first way to change energy of the phases, the decrease of enthalpy, and second way is decrease enthalpy due to the transformation from liquid to solid, and it is interval CB, and it is equal to the latent heat of the L. This one. This way to change the energy during the solidification. Decrease the enthalpy, but by cooling, or it is a second way, and by the transformation from the one state to the another. It's the second way. And the governing the energy equation for heat extraction process can be can come from the Fick law. It's a diffusion law for species. You can see this this from the previous course. Kinetic process imaging. This is the second picture. And we have here B is the diffusion component, and dB is the coefficient, diffusion coefficient of B. CB it is the concentration of B, and it is the distance to diffuse. So if we success in dB is constant, the diffusion coefficient of the B component is unchanged. So we can put it out from the differential from this to the we can have dCB over dt equal to dB, and we can have the secondary differentiation of C is respected to the distance H. This the second fixed second diffusion law, and you can apply this to the in the case of the heat extraction. And you can for heat extraction you can write also very similar equation, very similar like this. But we have the extra term because of the latent heat, because of the latent. But the rest is absolutely similar to the fixed second law, diffusion fixed second law. Here, the A is the heat transfer coefficient. The temperature is the distance also. Here V the heat or mole extracted. Okay, and CV the specific heat per unit volume. And here, this one come from the latent heat, of the metal. So we can write the governing energy equation for the heat extraction. And the cooling rate, the very important parameter of the solidification process, can be deduced from the very simple heat balance. If you assume that the metal is isothermal at a very low cooling rate, and specific heat of the liquid and solid are the same. They can differ a little bit, but we assume that they are the same. So in this case, you can write this equation, the heat balance. Here we have the left hand side term is the external heat flow, and the sum of the right hand side we have the internal heat flow. External heat flow and internal heat flow, and they are equal. If we have the subject solidifying, so we have the internal heat flow from the inside to the surface, and external heat flow from surface to the environment. Okay. And we have A here. This is the surface of the component, surface, and V the volume. We have the delta S. C is the specific heat, the temperature, and this one this small t is the time. Delta S F latent heat per unit volume. Okay, per unit volume, per molar volume. And DFS, this one, it is a fraction of solidifier. So it comes from the latent heat, and it is because of the cooling. We have the internal heat flow and external heat flow, and because this is a heat balance, so they are equal. Okay. And if you prefer again to this graphic, you can have this one. The decrease in the enthalpy of the liquid solid due to the cooling. The first term is the right hand side of the equation. These are DC and BA. The decrease in enthalpy of liquid here the decrease in enthalpy of solid. The first term is the right hand side of the equation, and the second term, this one, is the decrease in enthalpy due to the transformation from liquid to solid. It's the CB interval, and it's the latent heat. This one. See? For the heat balance during the solidification process. So, and here we have dT over dt. This one. It is the cooling rate. It is the cooling rate. And this one, the chain of the solid fraction. Open the time. It's the solidification rate. Have cooling rate, solidification rate. In this equation. And this is the heat balance. And you can calculate the cooling rate from this. Very simple. You can calculate this. From this, you can have the cooling rate like this. Easy. Okay. And you have cooling rate. You have the solidification rate. It is the case of the volumic solidification. Like this. If the solidification occur in the entire volume, and it's as a reason we have the crystal, a lot of crystal embedded in the liquid. It's a volumic. The crystallization and solidification proceed in entire volume of the component. It is the case of the volumic solidification, and in this case you can find the cooling rate from the heat balance. We have the cooling rate and solidification rate. But it's only one kind of the solidification. It's volumic. We have another kind of solidification. It's directional solidification. So in this case, we have the solid and the liquid, and we have the interface between liquid and solid. And this interface advance toward the liquid, to the center. So in this case, the unit of the solidification rate is meter per second. Meter per second. See, in this case, the unit is different. Not meter per second. It's the fraction, solid fraction per second. There's no net, no clear. Here, in the case of the volumic solidification, there are no clear interface between the solid liquid. Like this. In this case, we have very net, very clear interface between solid and liquid. And solid, as the solidification process, this interface advance to the center, toward the liquid. So you can consider the unit as a meter per second, because it is a movement of solid liquid toward the center. So in this case, it's a directional solidification. You can have to distinguish volumic solidification and directional solidification. Okay. So in this case, how to determine the cooling rate or the relation between the cooling rate and solidification rate. In this case, we have a very complicated relation between cooling rate and solidification rate. But in this case, it is much much simpler. Okay. So in this see the cooling rate, you can add d to the numerator and the denominator. It no change, any change, but we add this d into the expression for cooling rate. You see, so this one, the first term is the temperature gradient. dt over d is the temperature gradient. Okay, and the second term, d over dt is the solidification rate. Okay, so you can rewrite this one as the 3 multiplied by v. So we have the cooling rate is proportional to the solidification rate, and the proportional coefficient, it is the temperature gradient. Physically, you can say that the cooling rate is proportional to the solidification rate, and the proportional coefficient, it is the temperature gradient. Okay. So here you have the 3 temperature gradient, V is solidification rate, or the moving speed of the solidification flow. Solidification, the interface between the solid liquid toward the center. And we have V is over dt. This one. But simply in comparison with the case of the volumic solidification, and it is the main model for studying the solidification process. And we determine in the solidification rate as the advance, the moving speed of the interface between solid liquid towards the center of the liquid. So we use this mainly in our course. Not this, but this one. Okay. So we have the cooling rate, the temperature gradient, and the solidification rate. Okay. And we have a very simple relation between cooling rate and the solidification rate via the temperature gradient. You can find the temperature gradient like this. In the interval D, you have the temperature profile like this. In liquid, we have the very small interval D, and in this interval the temperature can be changed a little bit when we have the dt, and the dt over d, we have the temperature gradient, and in this case, it's the temperature increase towards the center, okay, towards the liquid. So we have the positive temperature gradient. In this case, the temperature increase. So if it is a gradient time like this, we have the zero gradient. The temperature everywhere is the same. There are no gradient. And if the profile like this, the temperature is decreased. towards the center, you have the negative temperature gradient. So in this case, you have the positive temperature gradient. Positive temperature gradient. Okay. So we have the three kinds of the temperature gradient: positive, 0, and negative. Okay. So it is from the heat exertion, you can find can determine the cooling rate, very important parameter, solidification rate, also, and temperature gradient. It is very important parameter of the solidification processing, and you have to know. So, turn on the solidification structure. Because of this processing parameter, solidification rate, cooling rate, temperature gradient, and so on. It is a processing parameter, and they will determine the structure of solidification structure of metal or alloy. And if we consider the ingot casting, you can see the three zones of the solidification. Three zones. We have here it is the mold outside, and here we have the casting, ingot casting inside. It is ingot. So we have the three zones of the solidification behavior. The first one, it is the outer aqueous, this one. And this zone consists of the many small grains having random orientation and nucleated at the mold surface. Yeah. Very fine grain oriented randomly. It's the outer aqueous zone. This one. And after first very short time, this zone can be formed, and we can count this zone as a skin of the casting. Casting skin. After this, the second zone can be found, the columnar zone. This one. You can see the grain in the form then dry, and they develop towards the center as the column. So we have the columnar zone. And because of the can be formed because between the randomly oriented this outer aqueous grain. So because they are randomly oriented, so only grain from this outer zone can be developed if they are oriented very good. So what is the good orientation of the grain here? The good orientation, it is a parallel, anti-parallel to the heat flow orientation. Okay, it is a preferred flow direction, parallel and opposite to direction of heat flow. So they can develop into the columnar center, columnar zone, columnar dendrite. So it is a heat flow direction from center to the environment, and only the crystal which have the preferred flow direction, anti-parallel to the heat flow direction, parallel, but if opposite can be developed, can grow, okay. And from the columnar zone, columnar dendrite, columnar grain. So it is because of the competitive growth. Competitive growth. So, and finally, we have the inner. We have the outer equiactic zone and the inner equiactic zone in the center of the casting. Because of the maybe because the growth of the some diagram maybe broken, detached from the dendrite and go to the center, to the man, and serve as the nuclei for development of the equiactic, but very but much coarser than in the outer. And they can develop, they can grow in the man, the leaky, and the pool, slightly in the pool. So we have the three zones of the solidification structure. Outer equiactic, verify, columnar zone, and inner equiactic, much more coarser. And why the columnar zone can be formed? Because of the competitive growth, and only grain with the preferred direction, growth direction can be developed, and other no. So we can have the columnar like this. You see, they develop in only one direction. This direction is parallel to the direction of the heat flow, but opposite. Three zones. The ingot custom. So normally we have this. We have outer equiactic piston. Great. We have the columnar zone. And in the center we have equiactic also, but coarser. It's outer is very fine. The inner is much coarser. It's a normal structure. Can distinguish very clearly three zones. But the microorganism can be other from this, different from this, like this. Like this. We have only two zones. Outer equiactic very fine grain, and only grain, only columnar. There are no inner equiactic. It's very good for some preferred for some functional material. For example, magnetic material. We must have this structure. But for construction material, we prefer another structure. Only equiactic grade. It preferred for the construction material. It can be obtained by a semi-solid method technology. This in can gain the much better mechanical property. If the grain is equiexist in the entire volume throughout volume. But we have to apply some special technique to obtain this microstructure, and namely it is a semi-solid technology. Conventional. Normally, in the conventional method, we have this. Structure, 3 zone of microstructure. Okay. So this one is preferred for functional material. This one preferred for constructional material. And to obtain this microstructure or this one, we have to apply some special technique. If in the case of the conventional solidification process, we have this. We have 3 zones normally. Yes, no. And this solidification pressure depends very much on the liquid solid liquid interface morphology. And in the case of the pure metal, this one. In this case, what do we have? We have the columnar crystal. In this case, okay. In the case of the pure metal, the interface between the solid and liquid is planar. Okay. Absolutely planar. And the grow in the direction anti-parallel to the direction of the heat flow. It's a interface liquid solid interface is planar, and this crystal will be developed in grow anti-parallel to the direction of the heat flow. In the case of pure metal, if the crystal is nucleated in the mold or and grow from the mold one toward the liquid. In this case, we have very flat planar interface between liquid and solid. In this case, we can say that there are no solidification structure. This case, no solidification morphology. In the case of the equiexist crystal, like this, the equiexist crystal in this case. Okay, so you have the equiexist crystal in the pure metal. In this case, crystal is a dendritic. Dendrite. It's not dendrite. It's not any morphology. But in this case, we have the dendrite. Okay. And they can grow in all direction as a heat flow. Okay. In this case, only one direction, anti-parallel to the direction of the heat flow. But in this case, in the case of the equiexist solidification, the crystal can grow in the own direction, and the same direction as the heat flow. In this case, anti-parallel. but in this case, we have the same direction. The grow direction is the same as the direction of the heat flow. See the difference, very different. And here we have the aqueous and dry. And in the growing of the methane in the pure methane, it's controlled by the heat flow. There are nothing other, only heat. Heat is extract from the getting to the environment. Only heat. In this case, but the difference. In this case, heat is from liquid to solid through the mole and to the environment. You see? So in this case, the heat is from liquid to solid. From liquid to solid. But in this case, in the case of the aqueous solution, so the crystal is embedded in the man, and they can develop only if we can extract the heat. Okay, and we know that heat is transferred from the location with higher temperature to the location with the lower temperature. So the crystal must have the highest temperature. You can see here in this picture, if you can see the temperature profile. So the liquid have the highest temperature, and the temperature is decreased from liquid to solid to the mole and to the outside environment. But in this case, because the piston is embedded in the man, so if they can transfer heat to the environment, so the piston must have the highest temperature, and the man must be undercooled. So the liquid must have the lower temperature. So the heat can be transferred from the piston to the liquid and through the mole to the environment. See the very large, very great difference in these two cases. You see, and the grow direction of the piston is the same of the direction of the heat flow. So in this case, liquid have the highest temperature. In this case, solid piston have the highest temperature, and temperature will decrease because liquid must be undercooled. So you can pay your attention in this. You can, in this case, you have the positive temperature gradient. Temperature increase towards the center, towards the distance from towards the man. Temperature increase. But here we have the negative temperature gradient. Temperature in the liquid is decrease like this. And because in the case of the pure methane, you have only heat extraction. So this process solution is heat flow control. So you can distinguish very clearly two kinds in the pure method. Columnar certification like this, and the equiactive certification. This is in the case of the pure method. In the alloy, you have the different picture. In the alloy, you have the solute or alloy element, impurity. They are present. So we have the columnar crystal. In the case of the columnar, we have the dendrite. In this case, we have no morphology. The interface is planar between the solid and liquid. Okay. But in the case of the alloy, we have this interface is unstable, and they can they develop into the dendrite. We have the columnar dendrite. And but the growth direction are the same. Anti-parallel to the direction of the heat flow. The same as in this case. The same. Okay. We have the dendrite, columnar dendrite. But we can pay our attention in the acid flow, the diffusion, because the solid, we have some they reject the solute. So we have the diffusion flow from solid to liquid. So you have three. You have here you have two flow. Heat flow from liquid to solid and to the environment, and the solute flow from liquid to solid. Heat flow of the alloy element, because the solubility in the solid is lower than that in the liquid. So we have the solid reject the alloy element solute. So we have the diffusion flow from solute to liquid, from solid to liquid. So heat from liquid to solid, the solute from solid to liquid. Have to flow. In this case, we have the heat from solid to liquid and to environment, and solute alloy element the same, also from the solid to liquid, as in this case. But the heat flow is changed in the direction. In this case, from liquid, solid, to the mole, to the environment. But in this case, from solid to liquid, the same direction as the diffusion flow. So in this case, you have both heat and solute from solid and liquid. And in this case, the process is the solute diffusion control, not heat diffusion control, but solute diffusion. In this case, in the case of the columnar dendrite, in this case, it is much more complicated. In the case of the equiactive dendrite, and this the solidification process is controlled by the heat plus solute diffusion. See, in this case, only this is the pure method. Only heat flow control. Heat flow control. In this case, only solute diffusion control. But in this case, both heat flow and solute diffusion control, and very complicated. Very complicated. In the case of the alloy. In the case of the aqueous and dry. And we can note that in the case of the columnar, well, in this case, the hottest part of the system is the man, is the liquid, and heat from liquid to solid to the vapor. But in the case of the aqueous solidification, this one, the piston has the highest temperature. And it means the liquid, the man must be undercooled. So the aqueous crystal can be formed and developed. Very, very important feature of the aqueous solidification. You can compare between the pure metal and alloy. In the case of pure metal, we have the direction, flow direction. In this case, anti-parallel to the direction of the heat flow. In this case, the same direction. In the case of the aqueous solidification, it's called pure metal. For alloy. In this case, because of the some solute, some alloy element, you see here, the liquid solid interface is planar and very stable. But in this case, in the case of the alloy, see, the solid liquid interface not planar, not stable, and because of this, we can have the dry. Here there are no structure, but here you have dry, and we can have the diffusion flow from solid to liquid. Solid reset the solute, the following element, and the grow direction is anti-parallel to the direction of heat flow, but the same of the diffusion flow. So in this case, heat from liquid to solid, but solute from solid to liquid. It's a columnar solidification, columnar and dry. In the case of the aqueous and dry, we have the solute diffusion flow, heat flow, and grow reaction are the same. On from solid to liquid. On from solid to liquid to the environment. See, in this case, the direction of heat flow is changed from liquid to solid to solid to liquid. We have the same direction of on flow, diffusion, heat, and the grow, the same direction. In this case, we have the Q is the upper part. You can distinguish, can compare the solidification in the pure metal and alloy. So in this case, in these three cases, we have the solidification structure, and mainly it is the dendrite. In this case, we have nothing. There are no structure, solidification structure in this case. It's case of pure metal. If you compare the cases. and this one heat flow control in the case of the pure method. In this case, the solute diffusion control. Solute diffusion. In this case, heat flow plus solute diffusion. Most are complicated. And in this case, A and C, you have directional suffocation, and you have the columnar grain. Maybe a columnar grain or maybe columnar dendri. Dendri is also the grain. So you have the columnar grain, A and C. And B and D, we have the equiacid suffocation, and you have equiacid grain. B and D. See, you can see the difference between 4 phases. Okay. And the form of suffocation microtexture depend not only upon the cooling condition but upon the alloy composition. Cooling condition, it is a processing. In the alloy composition, it is a chemistry. Like this. We have the phase diagram. Aluminum and aluminum to copper. We have theta phase. Here you have alpha phase, aluminum, and theta phase is Al2 copper. We have the phase diagram is authentic. So in this case, you have 2 kinds of the alloy metal. 4, not 2, 4. You have A, and you have 2 kinds of the 2 basic grow morphology. It is the dendrite and authentic. Here, we have authentic composition, and before we have the hypoauthentic composition. Here we have hyper. Okay. So A, it is a pure metal, pure substances, and they can solidify in the planar or dendritic manner, like this. Planar or dendritic is for pure metal. FB, pure metal. FB is the solid solution dendrite. Beta or interdendritic precipitate. Yeah, B. Because its composition is do not exist. Solubility curve. Yeah. On the solute, on the alloying element, on the alloying atom, is in the solid diffusion. Okay. There are no precipitation. No precipitation. This is alpha. It is you can say it is a rod alloy. And C, it then dry plus some precipitation. Interdendritic, authentic maybe, and maybe some precipitation. We have D, authentic composition. See, we have the casting alloy. We have a hypoauthentic, hypoauthentic, and authentic alloy. All of them belong to the casting. Rod, casting, and pure. Here we have only planar or dendritic. For rod alloy, have only solid solution. there are no precipitation. And from this occasional you can have the precipitation. We have some maybe authentic between the dendrite. It's the interdendritic authentic. And the full authentic here is the composition. So the solidification structure depend on the processing parameter, okay, and the composition, chemical composition. And you can see some example of the it is the same picture, and you can see the precipitation normally located in the grain boundary, and you can see the some dendrite in the leaf, and dendrite in the base, nickel base along, and it is the outer dendrite. You can see it is the columnar dendrite, like this. The dendrite growing on this. Here has the equiactive dendrite growing on the direction. It's outer dendrite. It's some picture you can see. And you can consider some effect of the chemical composition on the solidification structure. In the example of the iron and carbon phase diagram. Know this? How come? You must know this phase diagram. And if the content of the carbon is about 1.8%, yeah, you can have the cementite, the pearlite texture. Yeah. From the alternate, we through the alternate reaction, we have the ferrite plus cementite. Ferrite plus cementite from alternate. We have this is the pearlite. We have cementite like this. Here, cementite, and here we have the ferrite, and they grow from the alternate. If the content of the carbon is low enough, 0.8%. So if the content of carbon is much higher, maybe 5.5%, you have absolutely another structure. We have the primary cementite, like this, and within them we have the ladybird. It's we have the alternate grain embedded in the cementite. So again, depending on the content of the carbon, we have absolutely different texture. It's the example of the effect of the chemical composition in on the solidification structure. Very clear. Okay, so we can see the process of the aqueous solution of dendrite and authentic or pure method or single phase colloid. Only from liquid, only one phase can be formed. Like this. The nucleation, the nuclei can be developed, grow until they impinge each other. It is okay. Firstly, we have the nuclei formed initially. They can unstable and grow into the dendrite. okay, and the dendrite can be impinged each other. It's a dendrite coherency. And at this moment, the dendrite cannot be developed anymore because no space. They impinge already each other, and we have grade can be found here. Okay. In the case of the authentic, we have the authentic reaction from liquid. We have the two or more solid phases simultaneously formed at once at the same time from liquid. But initially only one phase. Initially only one phase can be found. It's primary phase. Primary phase. And the second phase, nucleate in the primary phase immediately. So we have the we say that the liquid the authentic reaction in the two solid phases can be formed at the same time from liquid, but in reality the one phase primary phase informed firstly, and the second phase informed in nucleate in this primary phase at once, and they develop, they grow together to form the authentic grain. And in the viên casting, this authentic and then dry can be formed, can exist together, can develop together. You can see in this picture, macro structure picture, you can see the alpha phase and the authentic. They can develop together in the reality. In the solidification, both grow form, dendritic and it can be developed together. Maybe only authentic, maybe only dendritic, but in general, they can develop together. We can see both form of the solidification texture in one sample specimen. You can compare between the dendritic and authentic solidification. Here it is dendritic, here also authentic solidification. Okay, and we will end the lecture today for today. So it is the introduction. Okay, finish.
Yes.
So we who understand what I say, what I said, what I teach.
Almost.
Okay, so I will upload the slide, and we can we can read more. Okay.
Yes.
Okay.
Thank you.
Okay. So goodbye.
Goodbye, teacher.
Goodbye, teacher.
See you next week.
See you.
Bye, teacher.
What?
Goodbye,
Okay.
teacher.
Goodbye. I will log out. Okay.